Hello. In this lesson we're going to be looking at finding roots of complex numbers. For example, square roots, cube roots, and so on. Remember that every real number, or every positive real number, has two square roots. So for example, the square root of 4 is plus or minus 2. That's going to be the same for complex numbers as well. Every complex number is also going to have two square roots, but we're going to see that they will also have cube roots. They'll have 3 cube roots, 4 fourth roots, and so on. There is a formula for these, but instead of doing the formula, let's just introduce it with an example. Let's try and find the cube roots of the number 1 plus I. That means we're looking for a complex number, z, such that its cube is equal to 1 plus I. So we're solving the equation z cubed equals 1 plus I. And the trick is, since powers work much more naturally in polar form than in real imaginary form, we're going to write that number 1 plus I in polar form. Its modulus is root 2. Its argument is pi over 4, 45 degrees. Now, as we'll see in a minute, to get all possible cube roots, there's going to be 3 of them, we need to take all possible values of the argument of that complex number. Pi over 4 plus any integer multiple of 2 pi. So for example, pi over 4 plus 2 pi, pi over 4 plus 4 pi, pi over 4 plus 6 pi, and so on. So here k stands for any integer. In this particular case, finding roots of complex numbers, we need to consider all possible values of the argument. Simplify that. Z cubed is equal to that number in polar form, so now I can take the cube root of both sides, raise both sides to the power 1/3. Now I'm just using the rules for powers. 2 to the half to the 1/3, that's the powers multiply, that's 2 to the 1/6. The 1/3 power of the exponential, again the powers multiply, I get e to the I pi over 4 plus 2k pi all times a third. Plugging in different values of k, 0, 1 and 2, will give me the 3 different values of the cube root of 1 plus I. Let's try k equals 0, that gives me z naught equals 2 to the power 1/6 e to the I pi over 12. For k equals 1, I get 2 to the 1/6 e to the I pi over 4 plus 2 pi times a third. That's 2 to the 1/6 e to the I 3 pi over 4. Put k equals 2, I get 2 to the 1/6 e to the I 17 pi over 12. I've got 3 different values. Those are the 3 different complex numbers whose cube is equal to 1 plus I. I could try other values of k, but if I kept going and did k equals 3, I'd just be back to z naught again. And then z4 would be equal to z1 and so on. I'm not going to get any new values. Let's plot the roots in the complex plane. There was 1 plus I. That's the number I'm looking for its cube root. Here's the first one. Its argument was pi over 12, so that is 1/6 of a right angle. Here is 3 pi over 4, that's 1.5 times the right angle. And here is 17 pi over 12, so that's pi plus 5/12 pi. Notice how they all have the same modulus, 2 to the 1/6, that's what, 1.15 or something. And the arguments increase by the 2/3 of a circle each time. So what I've got is 3 equally spaced points on a circle. So every complex number has 2 square roots, 3 cube roots, and so on. Has n nth roots. The roots all lie on a circle. The radius of that circle is the modulus of w to the 1 over n, where I'm finding nth roots of w, and they are all equally spaced in argument.